The second type of, the second way to buy online ads is a non-RTB programmatic. And this is basically the same as the previous one. The only difference is that it happens in online space. And the third one, and for us the most important one, is RTB. RTB stands for real-time bidding, and it basically represents an online auction. So when a user opens a web page, oh, it's not much to be seen, but when you open a web page containing a banner, behind all this happens an auction. All marketers place their bids, and the highest bid wins. The winning ad is shown then to the user. With this approach, and with the fact that it is fully automatic and it happens fully in the online space, we are able to enhance and adjust this system by placing bid multipliers to adjust the bid heights for each user or for each website. AdForm is an online advertising technology, and it is one of the largest in the world. And thanks to the fact that it is private and fully independent, we are able to obtain entire information about the ads we have bought, uncensored, and the full information. The information looks like this, where each line represents a single banner, a single impression, as we say. We obtain information about who saw the ad, when, on what page, and also if the user interacted with the ad, if he has clicked on the banner, or if the ad was visible at all, and for how many seconds. The last important information we get from AdForm is tracking points, which represent our goals. We can describe tracking points as, for example, that a user has come to our website, or a user has come to our website and took our loan. And from AdForm, we get the information of cookies of users that has hit our track point, so that has marked our goal. So now a little overview of how AI works. We download the data from AdForm into our data lake, and we pre-process the data so that we obtain what we call user journeys. So we process the URLs that a cookie has visited to obtain a list of tokens that represents the cookie interests and topics that the cookie might be interested in. Using this information, we are able to apply a scoring algorithm, and once we use the user journeys and match them with a target, so whether the cookie has hit our tracking point or not, so has taken our loan or not, we are able to apply this information into a machine learning algorithm and then get a list of cookie IDs and their corresponding bid multipliers, which represent our computed affinity of each cookie towards our goal. So we could represent it as the affinity of the cookie towards our topic or towards our interests. This we call a cookie list, and upload it back to AdForm so that it really helps our customers, so that it is really applied doing the real-time bidding. And the last step in the solution is automating it, because we want this solution to be run every day at midnight to apply the most contemporary information, to score the cookies, and to apply it. And now we will get to the solution itself a little bit deeper. The first step is dataset creation. The first step of dataset creation is filtering by date. The filtering is done two ways. And the first step is to filter by date, because we don't want to use all the historic information. We only want to train on the past 30 days or 90 days, depending on the size of the customer. And also, the filtering by date is applied on each impressions, because we are only interested in impressions that happened before a tracking point was hit and not after. And then we group the information by cookie ID. so that we obtain a data frame looking like this, where we have a cookie ID, then concatenated domains that the cookie has seen, that the cookie has visited, and the target for that particular cookie. Second step is pre-processing. And then we apply tokenizing, because the URLs itself cannot be inserted into any machine learning algorithm. So we apply regex tokenizer to process the URLs into an array of tokens. And you can still see that it looks better, but still contains some noise in this case. So the next step is to remove stop words. And then we obtain real tokens that represent our interests or topics. The list of unwanted tokens that we use contains two parts, we could say. The first part consists of general stop words of English and Czech, such as and, me, who, that are really general and are present in articles about any topic. And the second type of tokens that we want to remove are URL-specific tokens, such as HTTPS, www, and so on. The third part is feature engineering. We apply count vectorizer on the list of tokens we have obtained, so that we turn this interpretation into a numeric vector that already can be presented to a machine learning algorithm. But what we do next is that we apply IDF, which stands for inverse document frequency. And basically, we incorporate it into the algorithm, this metric, because it allows us to gain more information about how unique or how common the token is. So for example, consider Seznam. I believe that every cookie could have it many times present in their user journey, but it doesn't give us many information, and it's not of any use for us, because it would be present in our target group, but as well as in the entire population. And the final step, and the main part, is model training. We have evaluated 5 types of models, featuring logistic regression, naive bayes, random forest, decision tree, and XGBoost. And to evaluate the models and pick the best one, we have used grid search, and for that we used train validation split. We decided to use train validation split instead of cross-validation due to the amount of our data. And in our model training, we also use MLflow. We use MLflow for 3 main use cases. The first one is to log parameters, artifacts, and models. The second one is to compare models. When multiple runs, you choose and you can click on compare and then see each of the runs and the metrics you have logged, or even visualize their matrices compared on each other. And the third reason why we use MLflow is to apply the model in practice and to make it easier, because now we can use only the URL. So if I have multiple models and I pick one that I want to use, I only need to copy its directory or its location, and then it's very easy to use it. We have used an interesting evaluation metric because, well, in this case, false positives and false negatives don't hurt us so much, because what happens is that a user is shown an ad he is not interested in or otherwise. So what we use instead is called a lift curve. And if you take a look at this graph, what basically the lift curve says is that if we score the entire population according to our affinity or to affinity to our goal, and then sorted them from the most affinite to the least one, and bucketized the users into n buckets, so for example 10 in this case, and then applied quantiles, so this is a centile and so on. And we can use this metric to to say that if I target my campaign on only the 10 most affinity % of population, I am 4 times more likely to hit my target. Or in this case, if I target my campaign on the 30% of the population of the top 30, then I am more than 2 times more likely to hit my target audience. Here you can see the model comparison on Lift 10 and Lift 100. For Lift 10, the worst performing was decision tree, and the best performing was random forest. For Lift 100, the worst performing was, quite surprisingly, naive bayes, and best performing random forest. And once we had this solution ready, we decided to apply a few further improvements. So the first one we thought of was extracting UTM parameters from the URL and then tokenizing the URLs without it, because UTM parameters are just tracking, added tracking parameters that don't give us any additional information about the topic, about the articles. And surprisingly, the lift decreased. The second extension we tried was decoding special characters and then deaccenting them, for example, in Czech. It's very important. And what we saw was, again, a decrease in lift. Just a slight, but still. And the third improvement we tried was replacing count vectorizer with Word2Vec model. What we saw was a huge decrease in speed. So we decided to stick with count vectorizer because we really value the speed of the solution. But also, it didn't perform really well, so we find out that Word2Vec model cannot extract any information, any context information from just the URL. But we use it in our other solutions and train on the entire articles, it works perfectly. But on the URLs just don't get enough information. And well, that's the solution itself, but is the solution perfect? We are able to compute the affinity of users towards a goal, and it allows us to target ads onto customers that are probably likely to be interested in our topic. And also, if we buy an ad for a user that probably doesn't have any interest in what we sell, then we at least buy it for less. So it's still a plus. On the other hand, a lot of cookies dies every day, and a lot of cookies are created every day. So we thought that maybe a better solution would be to automatically run the entire pipeline every hour. And another possible drawback is that we could overwhelm high affinity users with our ads. So if we apply the bid multiplier of 1.2 or even 2, then the user could be getting more and more our ads and would be probably disgusted by the brand at all. And that's all from me, and I'll be happy to answer your questions.
Thank you very much for the interesting talk. Is there any question from the audience right now? I'm sorry, we have only one microphone, but we are trying to solve the issue. But
Okay, thanks for the presentation. I have a couple of questions. I'm really sorry I have to miss it, but what do you predict? Would your machine learning models predict? A click on a banner, or what's the target value? What do you predict?
So the question was what we are trying to predict, and it's different for every customer, but it is always the tracking point what is set. So the customer always sets a tracking point, the goal that is important for them, and it could be just a visit of their website, or it could be, for example, on Alza, that a user adds a fridge to their basket, or basically anything you specify on your website. Any action. Any other question? Super.
Thank you. The second question is the cookie solution for the tracking users are going to disappear. those third-party cookies, well, in 2 years, I think it will be done. So how do you deal with that?
That's a good point, and we are definitely thinking about it every day and reading articles about how it's going and what we can expect. And well, the solution, we are trying to just augment slightly to, instead of bidding on cookies, to bid on websites themselves. So we then just place bid multipliers for every website based on the topic or on the percentage of people that have hit our goal. How many people of our target go there. So basically on Seznam, many people that have hit our goal go there, but also the entire population, so that's not of any use for us. However, for example, if I were a bank and I would expect my users would go to, I don't know, finance.cz or something like that. So this idea we took into the data and tried to build the solution this way.
Okay, thank you very much. Just one thing. Oh, sorry. Thank you. So your features are just words. It's a bag of words. Okay, you have IDF, but so for this model with features like words, I would expect the trees algorithms with very poor results, because there are millions of features, because you can have a dictionary of size of millions of words. So I would expect that, for example, Word2Vec should be much better. Should produce much better results than that. So I'm not sure why do you have such. Could you comment on that?
Yeah, sure. And
sorry, I have too much words in my head.
Yeah, I get that. Well, I think that the reason why Word2Vec performed so badly was also because of the count of features I used. And well, we compute in clusters, and that costs money, not us, but also our clients. So, well, first of all, the speed that we create the solution is important. A client doesn't need to make a perfect solution in 1,000 main days. And also, an important factor is the speed of the solution itself. And by increasing features for the Word2Vec model, I increased the number of features, and the accuracy or the lift increased, the performance was better. But once I have reached a certain number of features, it was so slow that I didn't see any point in going further. So I would, even slow it down even more.
Okay. Any more questions? No? Okay, then we will continue with the Slido question. Stay here, please.
Sorry.
There are some more here.
Okay.
So we'll start with the first one. Have you considered using deep learning techniques as well?
Yes, we have, and well, it's in our to-do list, but the to-do list is quite long, so it's definitely what we have considered, but we just haven't gotten to it.
Okay. And one more question before we start with the next talk. What do you think is the reason for such poor results of native bias?
Well, that's a really good point to notice, and honestly, I don't know. Partially, it could be due to the fact that the dataset was split differently for every classifier type, but I don't expect all the reasons to be just because of this issue. And I didn't think of any or didn't find any other reasons or any other aspects, really.
Okay. Okay, so we will start the next talk. So thank you very much for your talk again.